Alright, in this example we look at a line integral of a vector field. Here is our particular vector field given. It's a two-dimensional vector field, and you can see it down here in the picture below. Here are all the different vectors which make up this vector field. So sometimes the vector field is pointing to the left, sometimes it's pointing to the right, sometimes you can see the vector is pointing even down. So we've got a wide variety of vectors that comprise this vector field. We have a curve given in this problem, and the curve is the top arc of a circle, so it's the top of a circle that goes from a point P to a point Q, and the radius of this circle is a radius r is equal to 1. Okay, and we'll go through the details in a second, but if you were to compute this integral, we're going to find that we're going to do some work to get 0 as our answer. So before we go through all the details, let's look at why we're going to get 0 as the answer for this line integral. Okay, so let's just focus again on the curve and the vector field. Okay, so we have here in black the vector field itself. We really need the vector field at those points on the circle. So if we're going to do a work integral, we need the vector field at the points on the circle. So here we can see here are 4 points on the circle, and here are 4 vectors that comprise the vector field at 4 points along the curve. Okay, there is also the vector we need r prime at t, which is the direction vector of the curve, and at this point the direction vector of the curve is the vector which points tangent to the curve, and here at this point the vector points tangent to the curve. At this point there is the tangent to the curve, and at this point there is the tangent to the curve. Okay, so what we need then is, once we have found the vector field along the curve and the direction vector of the curve, we needed to compute the dot product of these two vectors. And essentially what's going to happen there is we're going to look at the component of the force that points in the direction of the amount of the force that points in the direction of the curve itself. Okay, so here we have in pink, we're doing these projections, right? And so those are the blue arrows. Okay, and here is the blue arrow. And as we can see that the force vector and the direction of motion vector are on one half of the curve, right? The force and the direction of motion are in opposite directions of each other. So if we look at just the blue arrows themselves, we can see that there is the force pointing in the direction of motion is backwards in this case and forward in this case. And because the vector field is symmetric, we can see that the vector field is the same on this side as it is on the other, and we're traveling the same distance from here to here and from here to here along these arcs of the circle. We expect there to be a balancing out of the work done. So when you compute this force projected in the direction of motion, that the amount of work on the right side of the circle and the amount of work on the left side of the circle are equal and opposite. And that is why we kind of expect from this picture to get 0 for the integral. So that is just an intuitive kind of idea of why we expect the answer to be 0 here. So let's go through the details now of doing this integral. Okay, so we had a vector field given. This is a two-dimensional vector field. The vector field was 2xy, x squared minus 1. And in our curve, was the top half of a circle of radius 1, and so when you parameterize that circle, it would be best if you use sines and cosines, and t goes from 0 to pi in that case. I would really be wary. I know many people are really like the square roots description of circles. If you tried this, this could lead you to some bad integrals that you have to compute. Okay, so I really recommend using the sines and cosines. Okay, so we have our vector field, we have our curve, and we need to put these two together to compute a line integral of this vector field along that particular curve. Now we know that to fill in the blanks, we're going to integrate along the curve, and given our parameterization of sines and cosines, to get the top half of the circle, we only need to integrate from 0 to pi. The vector field along the curve is 2 cosine of t sine of t. Wherever there was an x, put in a cosine. Wherever there was a y, put in a sine. X squared minus 1 is cosine squared of t minus 1. There's the vector field at those points along the curve. And then we need to bring in our derivative of our curve, r prime of t, or the direction vector of the curve, and derivative of cosine is negative sine, derivative of sine is cosine. There is r prime of t. And then we need to do a dt integral after we compute the dot product. So we'll get the integral from 0 to pi. We'll get 2 cosine of t with a minus sign, sine squared of t, okay, plus let's see, and we need to do this cosine, distribute it through, plus cosine cubed of t minus cosine of t dt. Okay, so I'm going to pause for a second while I look at this integral. Alright, so after looking at this integral for a second, we can see that this is not the nicest integral to look at, but maybe there's some algebra that can be done to kind of simplify this a little bit. And if you factor out a cosine of t, you'll get cosine squared of t minus 1. And by the trig identity, sine squared of t plus cosine squared of t equal 1. Cosine squared of t minus 1 is equal to negative sine squared of t. So what we're finding here is that this quantity is the same thing as cosine of t times negative cosine of t times sine squared of t, right? Which means that we have 3 of these cosine of t sine squared of t terms. Okay, so this problem simplifies quite nicely, and now we are down to a u substitution integral that u is equal to sine of t, so du, derivative of sine, is cosine of t dt, and so that leads us to the integral of minus 3 u squared, okay, du, and then we switch our limits when these are t's, these are t integral, t limits. When t is equal to 0, u is equal to 0, and when t is equal to pi, u is equal to 0. So we have the integral from 0 to 0 of something, of an integrand, which means that our integral is equal to 0. Okay, so, excuse me. So rather than tackling a complicated integral here, we did a little bit of algebra, and it simplified quite nicely and then turned into a u substitution problem. So that explains, mathematically why we get a 0 for our integral, but we also can rationalize that answer in terms of the vector field and the symmetry of the vector field and the fact that our curve and the force vectors match up nicely to cancel each other out. So ends this video.